Hello, in this video we're going to talk about the definition of a group and why there is something slightly wrong with the definition of a group. So usually when we define something in mathematics, we make sure that we do not include extra stuff to our definition. What does that mean? For example, when you define a triangle to be isosceles, the way you define it, you say it's a triangle that two of its sides are congruent. You don't define it in a way that you also mention that two of the angles are in fact congruent. So you could either define it as a triangle that two sides are congruent or a triangle that two angles are congruent. You don't include both of them in the definition. Why? Because one follows from the other. But for some reason in the definition of a group, there's actually some extra stuff hidden in that definition. So let's talk about that. So first, what is the definition of a group? There are three properties that we need to check in order to check something is a group. Starting from a binary operation, which means hidden in there, we assume that it is closed, the operation is closed. We have associativity, which means AB times C is equal to A times BC. We have identity, which means there is an element that EA and AE are both A. And we have inverse, which means for every element, there is another element that their product is identity from either directions. Now, given that there doesn't seem to be any wrong with this because these three properties are completely independent of each other. Why is that so? In order to show that these three properties are completely independent, we have to come up with examples that satisfy two of them but do not satisfy the third one. So let's just start from an example that is not associative, but it has identity and it has an inverse. So consider the set of all non-negative integers 1, 2, 0, 1, 2, 3, so on. So this is our set, and consider A star B to be absolute value of A minus B. Now this is not associative. If you look at absolute value of 1 minus 2 minus 4, this is going to be absolute value of 1 minus 4, which is 3. But if you look at absolute value of 1 minus absolute value of 2 minus 4, this is going to be 1 minus 2, which is 1. So this is not associative. The first one is 1 star 2 star 4. The second one is 1 star 2 star 4. So this is not associative. But it does have an identity. So if you take any element A star 0 and 0 star A are both A because A is non-negative. This is for every A inside G. We also have an inverse. If we take any A, n by A minus A is also is 0, which means A inverse is A. So it has identity. It does have inverse, but for every element, but it is not associative. So that means we cannot deduce associativity from the other two conditions. Now, can we deduce identity from the other two conditions? That would be a little bit even silly, because if you were to deduce identity from the other two, you would need to know what there is an identity. So that's doesn't quite make a lot of sense. But even given that it's a little bit of a weird question to ask, can we come up with an example that everything has an inverse? So AB is equal to BA is equal to a fixed element, but that fixed element is not in fact identity. And the answer is yes. So what would be an example of a set that everything has an inverse, but that element is not identity? The simplest thing we could do is to define a set G. Basically any set, almost any set would work. Let's say the set G is 1, 2. There's two elements in here, and define every element for every A and B in G. Define A star B to be 1. So if you define it this way, then of course this is associative. So A star B star C is the same as A star B star C. Both of them are 1. So it is associative, but it doesn't have identity, because if you take A star B, let's just say E is an identity element. So A star E must be A. Both were 1 and 2, but we know that A star E, the way it is defined, is just 1. So that means it doesn't work for A equals 2. So that means it doesn't have any identity element. But everything has an inverse. You could say A star B and B star A are always 1. So therefore B is the inverse of A. But as I said, it's a little bit of a weird question to ask, because without having the identity element, we can't really talk about the inverse. Now the last question is, can we come up with an example that we do have identity but the inverse does not exist? And that's also pretty straightforward. We can come up with an example of the set G to be all non-negative integers with addition. So A star B is just A plus B. This is clearly associative. It does have identity. So A plus 0 and 0 plus A are both A. So it has an identity. And it also satisfies associativity. But of course, nothing has inverse except for 0. So 1 plus x equals 0 has no solutions. So in that sense, this definition is perfectly fine. So these three conditions, 1, 2, and 3, associativity, identity, and inverse, are completely independent of each other. But if you dig deeper in there, you see that there's a little bit of a flaw in that definition. What is the issue that I'm talking about here? So we have three conditions. The first one is associativity. The second one is identity. I can break up identity into two different identities. One of them is existence of a left identity. What does that mean? It means there's an element in G that for every A in G, EA is equal to A. So that's left identity. We could also write down a right identity. So that right identity means there is an element E in G that for every A in G, AE is equal to A. And then we could also break down the definition of having inverse into two different things: left inverse and right inverse. For every A in G, there is a B in G that AB is equal to, or rather BA is equal to identity, because this is the left inverse. And the right inverse would be something similar from the other side. For every A in G, there is a B in G that AB is equal to identity. Now we want to see whether these 5 conditions are also independent of each other. So interestingly, they are not independent of each other. So for example, we can drop 2 of these. For example, 2b and 3b can be dropped. So in other words, 1, 2a and 3a imply 2b and 3b. So in other words, we can kind of reduce our definition to something slightly simpler. So why is it the case that 1, 2a, and 3a imply 2b? So what do we know? We know that if I take an element a in G, then EA is A and BA is also E. So I know every element has an inverse and we have an identity element, but only a left inverse, not a right inverse. We're going to show that in fact B is also a right inverse. So we're going to look at AB. Since B is equal to EB, we can write this down as A times EB. And now we're going to write down E as BA. So this would give us A, B, A, B. Now what I have here is AB, the left side, is equal to AB squared, is equal to AB times AB. Now we are going to multiply by the inverse of AB from the left. So what we know is this. We know that there is a C inside G, that C times AB is equal to identity, and the reason is AB has a left inverse. So if we take these two, that gives us C times AB is equal to C times AB times AB, which means if we simplify this, we get identity equals identity times AB. But E is a left identity, so that means E is equal to AB. So what we just showed is that if BA is E, then AB would also be B, and that gives us right inverse, so 3b. So we implied 3b. Now we want to show that in fact AE is also identity. So let's write down AE. So AE is A times, I know E is BA, so we can replace that. By associativity, we can write it down as AB times A. AB is identity, so that would be EA, and EA is A. So that means in fact 2B is also satisfied. From 1, 2A, and 3A, we can imply the other two. So 1, 2A, and 3A imply that it's a group. Now we can drop two others. Similarly, if you drop 2A and 3A, it's just a matter of replacing right with left and left with right. That is also a group. So those two properties can also be dropped. Now if you look at these 5 properties that we have, 1 and then 2 that was part of 2A and 2B. This was 2. That could be broken up into 2A and 2B. And then 3 that could be broken up into 3B and 3A. In these 5 things, 5 properties, this cannot be dropped. We talked about that at the very beginning. So associativity must be kept. Now from these 4, if you look at them, there are 4 choose 2 possibilities. We can drop 6. There are 6 different pairs. We cannot drop 2A, 2B. We talked about why we cannot drop 2. So 2 cannot be dropped. 3 cannot be dropped. Those are 2 pairs that cannot be dropped. Now we can talk about 2A and 2A and 3A. We saw that those can be dropped. This pair can be dropped. And we saw that 2B and 3B, those 2 pairs can be dropped. There are 2 more pairs that are left. 2A and 3B, and finally 2B and 3A. So having a left identity, so this one is left identity, right inverse. So is it possible to have left identity and right inverse and associative but not a group? So here is now the question. Is it possible for G to satisfy associativity? 1, left inverse and right, left identity and right inverse, but not be a group. Okay, so let's write this down. So 1 tells you associativity, 2 tells you there is an element E that EA is equal to A for every A in G. The second one tells you 3B, tells you for every element we have a right inverse. So for every A in G, there is a B in G that AB is equal to identity. So the way we can actually define a set that satisfies those 2 things and also associativity is this. So let G be basically any set as long as you have more than one element, and then define this. Define A star B to be B. Now when you look at A star B star C, this becomes A star B is B, and then B star C is C. If you look at A star B star C, you get A star C, which is C. So in fact it is associative. Now we want to show that there is an identity. Well, there is an identity. Basically everything is an identity. If you look at 1 star A, and I'm talking about left identity, 1 star A is by definition A, so that means 1 is a left identity. But everything also has a right inverse, because if you look at 1 A star 1, by definition that's 1, so that tells us 1 is a right inverse of A. So from all these different combinations, we can drop 2A and 3A, we can drop 2B and 3B. In other words, we can either drop right inverse, right identity, or left inverse, left identity, but the others cannot be dropped. So this kind of shows you that a better definition for a group would be this, would be that a group is a set that satisfies associativity. It satisfies 2A, which is left inverse, left identity, and it also satisfies 3A, which is left inverse. So a better definition of a group would be this. Although it's obviously very common to include all of those as the definition, and usually this would be kind of as an exercise to check that in fact 2 of those conditions are not necessary. And this brings me to the end of this video. So I will see you in the next video.